All right, good morning. Hope everyone's been well since I've last seen you last week. Today we're going over Lab 4, Human Population Growth and the Exponential Growth Equation. So bouncing off of what we were going over last week with the exponential growth models, we're now actively using this equation and looking at the variables for different case studies, different questions, and how can we get two different variables using these equations. So first, moving on to the outline for today, we're going over the water resources data collection, so Lab 5A. Basically, it's this water use chart where for the next 7 days, starting today, you're going to be recording the amount of water that you use for different activities throughout the day. And then next week, using that sheet, we're going to be making some Excel charts and looking at your water resources, like how much water you use compared to the average US person, and compared to the people in our class. And I'll be going over how to fill out that sheet in the next few slides. But for today, we're going over just bouncing off again of the human population growth from last lab. I'm going to briefly show you around 8 minutes of the exponential growth equation. It's the growth equation that we're going over today. It's the same variables, different notation, but we're going to be actively answering some questions with it. And I'm going to go over some practice questions and then put you in breakout rooms to go over part A for the lab assignment for today and just answer those and do those calculations for that. And then afterwards, you're going to be, for part B of this lab, you're going to be looking at your ecological footprint. What is it? I'll be going over the concept of it. How can we look at global patterns between the US, developing countries, developed countries? What does it look like for countries with resources, and how would that affect per person their ecological footprint for that country? And then you're going to be taking an ecological footprint yourself, and I'll be putting you in breakout rooms to do that, to discuss your findings. So the deliverables for today. So before we meet for next class, you're going to be turning in your Lab 4 responses. So on the Canvas page for Lab 4, there is a Word doc with questions that you're going to be answering for part A and part B. So part A, we're going over the exponential growth equation. So that's a couple of questions using an equation and doing some calculations. And for part B, it's your ecological footprint. So you're going to be taking your ecological footprint quiz and then discussing your results on part B. And then before we meet for next lab, you're also going to upload your water use chart, which is 7 days worth of 1 week's worth of data. And you're going to fill it out and upload it to Canvas. And then that's all you have to do. Instead of a pre-lab quiz, you're going to be doing this water use chart for the next week. So the water use chart, you can also download that from Canvas. It's also under Lab 4, that link for Lab 4. Again, you're going to be recording your own personal water use for 7 days, and you're going to be filling in the totals for the week and then uploading it to Canvas before we meet for lab next week. And then afterwards, we're going to be going over how to fill in the Google Sheet with this data and then transferring it to an Excel sheet and then doing calculations or making graphs from there. But this is what it looks like when you download it. Off to the side, there's different water use activities like baths, showers, number of flushes per toilet, and then also in terms of like laundry loads, like how many loads of laundry are you doing, or if you're going to be washing dishes, how many minutes have you been washing your dishes for? And you were recorded for 7 days. If you say you didn't take a bath for like maybe you've taken like 1 bath for like on day 4, but you've taken showers for like the other days, you would just not fill in those days where you didn't do that water use activity. But as an example, a filled out version of this water use sheet would look like this. And at the top, yes, so you would tally up over this entire week, the number of flushes or how long you've taken your shower in minutes and all of that. And after the end of the week, before we meet for lab, you would add up your total events on the side here, and you would multiply this whatever number, this total events number, by gallons per unit. So for some of these gallons per units, these little boxes, there's two different numbers. So the one in the asterisk at the bottom are for low flow devices. And that's a general rule of thumb, is that if it's been replaced by the within your lifetime, within however long you've been alive, it's a low flow device. So you can just circle it. If not, you can use the original number for a non-low flow device and then multiply your total events by gallons per unit to get your total gallons consumed. And then after you've done all of these, after you've multiplied all of your total events by gallons per unit, you would just add in and get your total gallons used within 1 week. And then make a hypothesis about why do you think your number is this. Maybe you would think that, say for an hypothesis, my water use will be higher than my class's average because I did a lot of laundry. Or maybe I cooked a lot, so I had a lot of dishes to wash. So my water use would be higher than my my classmates. And at the top too, right under where it says name, you would also put in your residence type. So along with dorm, you can put in apartment or house or multi-story complex, something like that. So whatever residence type that you're living in, you would just fill out that part. But did anyone have any questions about how to fill in this chart?
Is this like per person or per household record?
I'm sorry, can you say that again?
Is it like per person, or like if you live with like your family, would you record for your family?
Try to record for your own, for yourself as an individual. But if you have, say if you're doing laundry for your whole household and you're just tallying up like, this is how many times I've done laundry, but it might be higher because I have, because I'm doing laundry for everyone, you can put that in your hypothesis too. Okay, awesome, great. So moving on, we are going to start talking about human population growth. So last week we talked about population growth and we looked at it in terms of moose and wolf populations, but now I think it's a little bit more interesting to see within ourselves, what would the trends look like for humans? There is going to be, I'm going to be showing you this video that's going to be going over the exponential population growth equation. So it's going to look a little different than the equation that we looked at last lab. It's the same variables that we're looking at though, just in a different notation. But again, we're going over exponential growth and just a review from logistic growth. But I will now share with you all that video, and you can also find it under lab 4. So if you go to the Canvas page, lab 4, there's this background information, and then where you would take your pre-lab quiz, there's this link. But if you go to just like scroll down a little bit more, your lab 4 assignment questions, which we'll be working on in the breakout rooms, is here. But the water use data sheet can be found here, and the video that we'll be watching is linked down here too. The full version is around 1 hour and 14 minutes, but we're just watching the first 8 minutes of it, and we can go over that now. So in this video, it's from this professor in the University of Colorado. He's a physics professor, and he's just going over the exponential growth equation and how would that look like over time in different situations.
Well, it's a real pleasure to be here and to have a chance just to meet with you and talk about some of the problems that we're facing. Now, some of these problems are local, some are national, some are global, but they're all tied together. They're tied together with arithmetic, and the arithmetic isn't very difficult. And what I hope to do is I hope to be able to convince you that the greatest shortcoming of the human race is our inability to understand the exponential function. So you say, well, what's the exponential function? This is a mathematical function that you would write down if you're going to describe the size of anything that was growing steadily. If you had something growing 5% per year, you'd write the exponential function to show how large that growing quantity was year after year. And so we're talking about a situation where the time that's required for the growing quantity to increase by a fixed fraction is a constant. 5% per year, the 5% is a fixed fraction, the per year is a fixed length of time. Now that's what we want to talk about, it's ordinary, steady growth. Well, if it takes a fixed length of time to grow 5%, it follows it takes a longer fixed length of time to grow 100%. Now that longer time is called a doubling time. We need to know how you calculate the doubling time, and it's easy. You just take the number 70, divide it by the percent growth per unit time, and that gives you the doubling time. So our example of 5% per year, you divide the 5 into 70, you find that growing quantity will double in size every 14 years. Well, you might ask, where did the 70 come from? The answer is it's approximately 100 multiplied by the natural logarithm of 2. If you wanted the time to triple, you'd use the natural logarithm of 3. So it's all very logical. But you don't have to remember where it came from if you'll just remember 70. Now, I wish we could get every person to make this mental calculation every time we see a percent growth rate of anything in a news story. For example, if you saw a story that said things have been growing 7% per year for several recent years, you wouldn't bat an eyelash. But when you see a headline that says crime has doubled in a decade, you say, my heavens, what's happening? Well, what is happening? 7% growth per year. Divide the 7 into 70, the doubling time is 10 years. But notice, if you're going to write a headline, you never write crime growing 7% per year, because most people wouldn't know what it really means. Now, do you know what 7% really means? Let's take another example from Colorado. The cost of an all-day lift ticket to ski at Vail has been growing about 7% per year ever since Vail first opened in 1963, and at that time you paid $5 for an all-day lift ticket. Now, what's the doubling time for 7% growth? 10 years. So what was the cost 10 years later in 1973? 10 years later in 1983, 10 years later in 1993. And what do we have to look forward to? Now, this is what 7% means. Most people don't have a clue. Well, let's look at a generic graph of something that's growing steadily. After one doubling time, the growing quantity is up to twice its initial size. 2 doubling times, it's up to 4 times its initial size. Then it goes to 8, 16, 32, 64, 128, 256, 512. In just 10 doubling times, it's 1,000 times larger than when it started. And you can see, if you tried to make a graph of that on ordinary graph paper, the graph will go right through the ceiling. Now let me give you an example to show the enormous numbers you get with just a modest number of doublings. Legend has it that the game of chess was invented by a mathematician who worked for a king. The king was very pleased. He said, I want to reward you. And the mathematician said, my needs are modest. Please take my new chessboard and on the first square place 1 grain of wheat. On the next square double a 1 to make 2. On the next square double a 2 to make 4. Just keep doubling till you've doubled for every square. That will be an adequate payment. Well, we can guess the king thought, this foolish man. I was ready to give him a real reward. All he asked for is just a few grains of wheat. Well, let's see what's involved in this. We note there are 8 grains on the 4th square. Now, I can get this number 8 by multiplying 3 2's together. It's 2 times 2 times 2. It's 1 2 less than the number of the square. Now, that follows in each case. So on the last square, I'd find the number of grains by multiplying 63 2's together. Now let's look at the way the totals build up. When we have 1 grain on the first square, the total on the board is 1. We add 2 grains, that makes a total 3. We put on 4 grains, now the total is 7. 7 is a grain less than 8. It's a grain less than 3 2's multiplied together. 15 is a grain less than 4 2's multiplied together. Well, that continues in each case. So when we're done, the total number of grains will be 1 grain less than the number I get multiplying 64 2's together. And my question is, how much wheat is that? You know, would That'd be a nice pile here in the studio. Would it fill the building? Would it cover the county to a depth of 2 meters? How much wheat are we talking about? The answer is it's roughly 400 times the 1990 worldwide harvest of wheat. Now that could be more wheat than humans have harvested in the entire history of the earth. And you say, how'd you get such a big number? Well, it was simple. We just started with 1 grain, but we let the number grow steadily till it had doubled a mere 63 times. There's something else that's very important. The growth in any doubling time is greater than the total of all of the preceding growth. For example, when we put 8 grains on the 4th square, the 8 is larger than the total of 7 that were already there. When we put 32 grains on the 6th square, the 32 is larger than the total of 31 that were already there. Every time the growing quantity doubles, it takes more than all that you'd used in all of the preceding growth. Now, let's translate that into the energy crisis. Here's an ad from the year 1975, and it asks the question, could America run out of electricity? America depends on electricity. Our need for electricity actually doubles every 10 or 12 years. That's an accurate reflection of a very long history of steady growth of the electric industry in this country, growth at a rate of around 7% per year, which goes with doubling every 10 years. Now, with all that history of growth, they expected the growth would just go on forever. Fortunately, it stopped. Not because anyone understood the arithmetic, it stopped for other reasons. But let's ask, what if? Suppose the growth had continued, then we would see here the thing that we just saw on the chessboard. In the 10 years following the appearance of this ad, in that decade, the amount of electrical energy that we would have consumed in this country would have been greater than the total of all of the electrical energy we had ever consumed in the entire preceding history of the steady growth of that industry in this country. Now, did you realize that anything as completely acceptable as 7% growth per year could give such an incredible consequence that in just 10 years you'd use more than the total of all that had been used in all of preceding history? Well, that's exactly what President Carter was referring to in his famous speech on energy. One of his statements was this. He said, and in each of those decades, more oil was consumed than in all of mankind's previous history. Now, by itself, that's a stunning statement. Now you can understand it. The president was telling us a simple consequence of the arithmetic of 7% growth each year in world oil consumption, and that was the historic figure up until the 1970s. Now there's another
So that video was a really good review on exponential growth and some background on exponential growth, but also that new equation that he mentioned to chart and look at exponential growth, that's the same equation that we're going to be looking at today. So just a review from lab 3, exponential growth, that growth model that we looked at from last lab, it depicts unlimited growth where we are assuming that there's infinite resources, no predators, no external changes, like as an example, there's no climate change. And it produced that J-shaped curve, which we saw in that video, but a logistic growth curve is the one, or a logistic growth model is the one that takes into account the environment's carrying capacity. So all of that unlimited growth, all those factors that would limit your population growth is taken into consideration, like there's limited resources, there is prediction, and climate change does exist. So that would limit your environment, the amount of space that you can spread out into, and it would produce that S-shaped sigmoidal curve where when it starts to slow down and where that growth curve starts to produce that S-shape, that's where the carrying capacity for that population is going to be at. So the exponential growth equation that the professor went over in the video is this equation, and same thing, same variables that we were looking at last lab, but now in a different notation, which we can use for part A for lab 4. So our equation here is n equals n naught times e to the kt. So what this means is that n is our population at this certain point in time. So our time is t, is equal to our n naught, so our initial population size for whatever time period we're looking at, times E, our inverse of natural log. So it's just this constant value that you can find on your calculator. If you have a scientific calculator, it's going to look like the inverse of natural log here. If you have a graphing calculator, it's going to look like the inverse of natural log on this side. If you don't have either scientific or graphing calculators, there are online calculators that we can use, and I will be sharing that link. But things like Desmos, Desmos is like an online calculator that you can use. But E is just the natural, or it's the inverse of natural log, and it's just this set number that you just plug into your calculator, and it's a constant value. So that's it's E to the power of K. This K is not our carrying capacity, it's our exponential growth rate, and it's usually given to us as a percent, which we're going to be changing into a decimal to do our calculations. And our K is multiplied by our time, so our time period that we're looking at. So as an example, if we're going to be looking at how to use this equation, we're going to assume that there's an exponential growth rate for future populations. We're going to try to find what is our global population in 2030. So our N is what we're trying to find in 2030, and we're given N naught. So our initial population size in 2010 is 6.07 times 10 to the 9 people. E is again the inverse of natural log. It's this constant value that's right on our calculator that we can just plug in. And then our annual exponential growth rate that we're given is 1.25%. So if we rewrite this as a decimal, it's 0.0125. And our time period, since we're looking at 2030, the population then, and we're given the population at 2010, it's going to be 2030 minus 2010 is our 20 years for our T, our time. So with all of these variables, if we're going to plug them into the equation, we can first write out all of our numbers that we were taking into consideration and plugging into our equation. So if we have our N equals N naught times E to the KT, if we rewrite that, we can write that as N is equal to 6.07 times 10 to the 9, which is that our N naught, our initial population size, times E, which is just that function, that constant value, to the K, which is this 1.25% or 0.0125 times T, our 20 years. So if you don't have a scientific calculator or a calculator near you, you can go to desmos.com/scientific and then plug all of this in. Say if we wanted, what that would look like would be this. Let me show you what it would look like if we went into Desmos. So if you just type Desmos /scientific into your Google search engine, it's going to look like this. And for this equation, how you would plug this in, it's very important, especially for things that have like 10 to the scientific notation. And so our 6.07 times 10 to the 9, we're just going to want to put things in parentheses so that it's very clear what number is what and what we're multiplying by. So if we're going to type this into Desmos, we can start by putting in our parentheses and 6.07 times 10 to the 9. If we wanted to put anything to an exponent on Desmos, we can use this function. And we'll just put that to the 9. We can indicate that that's a really big number. And if we're going to put in E, there's on this main setup for our Desmos calculator, there's this main function, there's ABC for where you can put in different letters, but there's also this function tool. So when you click on that tab, there's this E function where that's going to fill that in for us. And it'll give us to the exponent of whatever we want to put it to. And to our E, we're putting E to the exponent of K, so 0.0125. And we're going to multiply that by our time. our T 20 years. And so when you type that all in, they'll give us the answer, and it matches up to the answer that we know is 7.79 times 10 to the 9 people. So this is how we can use Desmos, and that's and this is also the number of people that is predicted to be on this earth by 2030. So back to, yes. I'm sorry, you're muted.
How did you get the E on Desmos? Sorry, I didn't really realize I was muted.
Yeah, no problem. So if we go back to, let me escape. So on the main setup for this calculator, there's this main tab, ABC tab, and there's this function tab. So if you click, so if you click on function, there's e to the whatever exponent that you can plug in. But if not, you can also click on this regular e function and then put it in the main tab. You can put it up to make an exponent and get that exponent function in there. But yeah.
Okay.
Okay, awesome. Great. So one great thing about this equation is that you can also rearrange it to find other variables too. So right now, we used it to find the population at a certain time, but now if we say we wanted to estimate the time that's passed during population growth, but if we're given the exact same variables, say n is equal to what we found, 7.79 times 10 to the 9 people, our n naught, our initial population, is again 6.07 times 10 to the 9 people. E is our constant value, which we're just gonna plug in by pushing a button on our calculator or clicking on that function within Desmos. Our K is again given as 1.25%, but now if we're trying to find time in years, we can set it up using this equation where T is equal to ln, and in parentheses our n, our population, over our initial population, n naught, in parentheses, all over K, our growth rate. So ln is now given instead of e. It's because the inverse of e is natural log, so that's where ln comes in. And if we're going to plug all of this in, we would look like this, where t is equal to ln, in parentheses, our n, 7.79 times 10 to the 9 people, all over our initial population size, are 6.07 times 10 to the 9, in parentheses, all over our K growth rate of 0.0125. And when we plug that into our calculator, into either Desmos or whatever calculator that we have, our T is given as around 19.96 years. And if we round up, that's around 20 years, which makes sense to us because if we're looking at the year 2030, the population then compared to 2010, that's our 20 years. So along with T, we can, referring back to that video, how the professor started talking about doubling time, this is how we can get doubling time equation. So if we're given a population, their initial size, say, was 1.00 times 10 to the 9 people, and it doubles to 2.00 times 10 to the 9 people, we can plug it into this original T equals ln over n divided by n naught all over K equation, but there's also an easier doubling time equation that's just T equals 70 over K. So given the exact same values, or given like our the doubled population, E is our constant value, and with the same growth rate as 0.0125, if we plug all of that into our original time equation, we can divide that n by our n naught. And since it's doubled, it would just be around 2 divided by 1, it'd be 2. So everything in this equation, or within this parentheses, would just turn out to be ln over 2, all over our growth rate. And if we plug in ln over 2, it's going to show up as this really long decimal where it's 0.693 and on and on and on, all over our growth rate of 0.0125. And if we multiply that by 100 to get our growth rate back into around like a decimal, if we would get 70 all over 1.25. And since our growth rate is k, we can just rewrite that as k. But if we were going to solve that, it would give us this number. But if we are looking at any population that doubles in size, to skip all of this, to skip using this time equation, we can just use t equals 70 over k. It's going to give you the same answer either way to get the time that's passed, but I think it's a lot easier to use this equation. So that's another way you can find time. Now, I'm going to show you the human population growth. So more specifically, there's like population clocks online that you can look at. And one of them is using data from the US Census, and the other one is using equations like a online calculator to look at your population clock. So if I was going to show you that, we have this. So this population clock is using data and all the numbers gathered by the US Census. And the US and world population clock, it compares the United States data along with the world population. And if we were going to look at, I think it's just pretty interesting to look at how a population within the world and the US is changing over time. So right now for the US, we can see that there's one birth every 9 seconds, one person passing away every 11 seconds, and then one migrant coming into the US every 666 seconds. So what that means is that every 40 seconds, we gain one person to our US population. And on the right side, we can see the world population and how that's changing over time. But the 10 most populous countries as of July 1st, 2020, being China, India, United States, Indonesia, Pakistan, Nigeria, Brazil, Bangladesh, Russia, and Mexico. And looking more specifically at the United States, we can see that this number as of July 1st, 2020, compared to now has changed quite a bit. But if we move down, it gives us more background information about, for the United States, the population growth by region. So we have Southwest, Midwest, and Northeast, but we can also scroll and see what's the United States population divided by age and section by different genders. So say around in your 20s in the US, there's around 0.67% of people in the US are in their 20s and are male. And around 0.64% of people in the United States that identify as female are in the US in their 20s. And if we scroll down, there's also more population or just more information on the population within states. So the most populous states on the bottom, we can see is the very first one is California, where we have around 39 million people in 2019. So per population per square miles, that would be around 253.5 people per square mile. And then onto the side, there's more information on high density, but this is one website that looks at population and charts the populations within like the US. But if we were going to now look at, but there are some limitations to the US Census and like how that would estimate population for us. So another population clock would be on that second link. So these slides are available to you too. So if you wanted to go into and look at these websites yourself, you can find that on Canvas within like the slides in the PowerPoint. So another type of population clock is this website where it's using data, using JavaScript 3.0. So it's this geographic browser that's created. This population clock is created by a professor from UC Berkeley, and it's estimating the population from any date between 1900s to 2100. And I think it's a little bit more accurate specifically because the US population or US Census Bureau, there's some limitations to what data that they can gather. But right now we can see as of today, 8:08 a.m., there is around 7.5 billion people. But if we wanted to look back in time, we can also do that too. Did anyone have like a specific date that they wanted to look up in the past? Like I usually ask for people for like if they wanted to look at their birth dates or something like that. If not, there's also this date that I like to refer to, which is May 1st, 1999. And this date is the first day that the first SpongeBob episode was aired ever. So in May 1st, 1999, there was around 5.9 billion people. And if we would unfreeze this and move forward in time to today, we can see that around 1.6 billion people have been added since then. And that is quite a lot of people. So yeah, it's very interesting if you wanted to look up this population clock later on your own time, and then say for look at your own birth date and see how much people have been added since then, you can. Now if we're going to go back to our PowerPoint. So we see that human population growth from two different population calculator websites, it's on the rise. And this is due to the artificial inflation of carrying capacity. So we saw that carrying capacity from last lab, it can be adjusted based on it changes based on different variables. And for us, it changes, and there's this artificial inflation where our carrying capacity is now higher than normal because of technological advancements. So if we're going to think about agriculture, or if we're going to like specifically for agriculture, the use of pesticides, herbicides, the fertilizers and things like that, they have helped us get or just make more resources or grow crops at a rate that wasn't possible before. And this has helped us in terms of population growth, where now there's more humans than ever because there's more resources from using this type of technology. But it's fertilizers, pesticides, all of that has an effect on the environment. It can be pretty damaging over time. So eventually, the effects of these techniques and these measures that we're using, we're eventually going to start feeling the effects of it. And so even though we created this artificial carrying capacity, eventually we are going to reach that carrying capacity, and that's going to mean something in terms of the effects that we feel, indirect or direct effects. And now we can start to look at our own resource usage, like moving forward. So what you can do now is work on part A in your lab 4 assignment. You can find that Word doc right in the lab 4 Canvas page, but I can just show you that really quick, but what I would suggest is opening up this PowerPoint and having the equations that I went over handy so you can refer to them. I'm going to put you in breakout rooms to work on part A, these couple of questions where you're looking at a couple of case studies to, yes, somebody raised their hand.
Yeah, it says on the assignment sheet that we should have the answer sheet. Is there like an extra doc that we have to put our answers on and like show our work?
Yeah, so if you're not here, let me just show you the Word doc. So the answer sheet would really, for this assignment, it's really just this Word doc. If you are comfortable using Word doc to put in your equations and do calculations and just type it up on here, you can. But if not, you can just write all of your work by hand and then just take a picture of your work and submit it that way. So if you did want to try putting in your equations on this Word doc, one way you can do that is if you just click wherever you want to start your equation, go under Insert. Right next to the Home tab, there's this Insert tab, and all the way at the end of this toolbar, there's this equation button. And if you just click on that, it's going to start your equation wherever you clicked on within your Word doc. So you can put in your work within and type in your calculations and your work into your Word doc this way. But if you're more comfortable doing writing it out by hand, you can do that as well, and just turn in a picture of your work then. But this is part A. This is the first page is the questions that you're going over. So for question 1, yeah, you're using the exponential growth rate, and then you're calculating just using the equation that we looked at over in the PowerPoint. And say for question 3, if given the annual growth rate of 1.5%, how long would it take a population of 5 times 10 to the 9 to grow to 10 to 10 to the 9 people? If you're thinking about these two numbers, we can see that it doubled over time. So for question 3, you would be using the doubling time equation. And as a heads up for question 4, when it says the current world population, this Word doc, it's referring to 2020. So that year that we're referring to is 2020 for question 4. But I can also go over more questions as you go along. But as of now, did anybody have any questions before I put you all in breakout rooms? Okay, great. So I will give you around 20 minutes to work in your breakout rooms. So that would be, maybe I'll give you 25 minutes or 21 minutes. So that will be at around 9:35. Before we meet back up again, I'll probably pop in and out and check on everyone's progress. But okay, awesome. If no one has any questions, let me just start making these breakout rooms. Okay. I will see you all at 9:35. I think you all did really well with part A and doing your calculations for that, but now we can go over ecological footprinting, which is your own footprint, the amount of resources that you use, and some background on that. So first, what is an ecological footprint, or an EF? So your ecological footprint is basically how much biologically productive land area is needed to support the resource consumption of an individual. So for one person, how much productive land do you need to support that person? So it's measured in global hectares, or GHA. And GHA, so around 1 hectare is around 10,000 square meters. To put that in context, that's around 2.5 football fields. So if we're thinking about the average US citizen's ecological footprint, that's around 7 global hectares. And compared to the global, like the average global human ecological footprint around the world, it's 1.7 global hectares. And these numbers are reported from the Global Footprint Network from the 2015 study. But I'm going to go over a little bit more what it looks like for developing and developed countries. What does that mean for countries with more resources, and what does more access to resources, and what does that look like for the ecological footprint? So first, if we're going to look at the world on this map, we have all of our countries laid out, and the darker the red, the darker the color, the greater the global hectares, the greater ecological footprint per person is for that country. So this was charted out in 2003, and again, around 1 global hectare is around 2.5 football fields worth of productive land per person. You can see that for North America, we have our darkest red. So usually in the more developed countries, the per person, per capita, their ecological footprint is going to be the highest. So the amount of resources that they use, because they have access to it too, is going to be higher. Now, if we're going to be looking at developed countries, so highly developed countries, this chart is showing us that. So this is from 2010. Across our X, our horizontal axis, we have different countries listed out, and across our Y is our ecological footprint in global hectares per person. And in the different colors, our key shows that there's different types of resources taken up by different colors. So our gray is in carbon, yellow is in cropland, light green is grazing products, dark green is forest products, light blue is fishing grounds, and orange is built-up land. Just some background on what resources or what's producing your ecological footprint with the different parts of that. So more specifically, since this is for highly developed countries for this chart, we can look at, say, the United States of America. So if we follow this one bar, we can see that there's most of it is in gray, which is in carbon. Some is in yellow, which is cropland. A little bit of it is in grazing products, forest products, and a small amount of it is in fishing grounds and built-up land. It makes sense to us because a big chunk of our footprint is in carbon because of the amount of fossil fuels that we use, the type of energy that we use that's powering our homes, but also based off of transportation, the type of cars and the fuel used to power our cars and things like that. And yeah, so in comparison, if we also look at this green dotted line across the bottom, that's the average, the world's average global footprint. So the average ecological footprint per person is this green line. So we can just keep that in mind for comparison, just to compare. So this chart is for highly developed countries, but now if we're looking at developing countries, we can see that their range or their ecological footprint is a lot lower. So this is for developing countries, and we can see the amount of carbon generally overall is a lot lower, and more of their ecological footprint is taking consideration things like cropland, so farming, agriculture, fishing grounds, and then forestry and grazing products and such. So it's the resources that they use and the amount of their ecological footprint in turn is a lot lower. And this has a lot to do with their income and then availability of resources and what they have access to. So now if we're looking at over time, did this change over time throughout the world? At the top chart, we have 1961, showing population in billions, ecological footprint per capita per person. And at the bottom, we have 2010, again in billions across the population in billions across our X, our horizontal axis, and our ecological footprint across our Y. In the different colors, there's the different colors indicate different countries. So we have in dark pink are North America, purple EU, light green other Europe, Latin America, and dark blue, light blue for Middle East, Central Asia, pink for Asia Pacific, and then orange yellow for Africa. If we're looking at 1961, this is our dotted green line is our global biocapacity per person, which is around 3.2 global hectares. And it was at this point just considering how much people we had at that time. So in 1961, we had around 3 billion people on the earth. And if we're looking specifically at North America, we can see that there's definitely a lot less, like than 500 million people, but the resource consumption, your ecological footprint is per person in North America is a lot higher. So it's almost at 7 global hectares, but maybe we can say that it's around 6, a little bit more than 6.5. But overall, there's like a lot less people, but their global footprint is a lot higher. And now if we jump to 2010, where at that point we were still under 7 billion people, but our global biocapacity, our global ecological footprint is now a lot lower. So in 1961, we had 3.2 as our global hectares. That's the ecological footprint that we can support at that point per person. But now it's at 1.7 global hectares because we have a lot more people. And with more people, each person also uses more resources. And if we're looking back at North America, we can see that there's still less than 500 million people in North America, but now the ecological footprint per person, so the amount of resources that they use, is getting higher. If anything, now in 1961, we could say that maybe it was a little bit more than 6.5 global hectares per person, but we can see now that it's maybe around 7, almost 7 global hectares. So in terms of yeah, the amount of resources used and over time by how much people is per person, the amount of people that's using the most, we can see that it's generally a small amount of people that's using the most resources. And now if we're thinking about income, the ecological footprint by national per capita income, we have our time on our x-axis, on our horizontal, from 1960 to 2003. And we're looking at our ecological footprint again through global hectares per person on our y. So we have our low-income countries in dark green. We can see that it's generally pretty stable. It doesn't really change over time. It's still generally pretty flat. So the amount of resources that they use in low-income countries don't really increase all that much. For middle-income countries, the amount of resources, their ecological footprint does increase a little bit at some points and drops at some points, but we see that's also pretty steady and it doesn't change all that much. But now if we look in dark red, for high-income countries, there are points in time where there are dips in the amount of resources that per person, each person uses, but there's a steady increase over time where more in high-income countries per person, they're using more and more resources. So that's something to think about. And the goal is to be both highly developed and also use a sustainable amount of resources. So this graph is based off of the UN Inequality Adjusted Human Development Index. So we're looking at inequality between people, and across the bottom, we are the chart goes from low human development, so developing countries, to very high human development, so highly developed countries. And across our Y is again our ecological footprint per capita and global hectares per person. In the different colors, we have our key shows the different countries. So we have, if we're looking specifically at this red dot, that's North America. And it's one of the few countries that's highly developed in the very high human development quadrant, but also has very high ecological footprint per person. So the goal is to be in this green box where you're meeting the minimum global sustainable development quadrant, where you're both very highly developed as a country, but also you have a sustainable ecological footprint per person. And a lot of, we can see that most countries in the low human development or developing countries, they have in turn a lower ecological footprint, but the goal is to be in this green box. And I think only one country has ever met the global sustainable development, where they are both highly developed and they had a sustainable ecological footprint. And it was Chile in around 2003 or 2010, but since then it's no longer the case. So we are still striving to meet this sustainable goal. Now, we are going to be looking at our own ecological footprint. So we were talking about developed countries and countries as a whole, but now if you go to the footprintnetwork.org, you're going to be taking your own ecological footprint and seeing the amount of resources that you use for yourself. So when you click into that link, it's going to look like this. And in the front page of the Global Footprint Network, they have this main page at the top, and right as you scroll down, you can click on Calculate Now to look at your own ecological footprint and look at your own impact. So when that takes us to a new page, this front page is going to show us across this little plane just a little interesting fact that for 2020, our Earth Overshoot Day is August 22nd, which is the Overshoot Day is basically that point in time where we've used one Earth's worth of resources within that year. And each person's Overshoot Day is different, but that's what we can also find out from taking this quiz. So if we click into taking the first step, we can, it's gonna ask us a couple questions about our own lifestyle. And for this very first question, say for food, how often do you eat animal-based products? So this quiz is as accurate as you, as much detail that you put into it. So if we wanted to say, we occasionally, very often, so meat daily, we can add details to improve accuracy. So say beef or lamb infrequently, cheese, dairy often, nearly every day, and adjust the details per each section accordingly. And then you can just save your response and then go through the ecological footprint that way. So what you're going to do from here is that this part is for part B. We are going to take this quiz twice, one for your USF, your San Francisco residents, and one for your permanent childhood residents. If they're the same thing, if those locations are both the same, you would only take this quiz once, and you can just write a sentence in your Word doc saying, my USF residents and my childhood permanent home residents, they're the same, and I only took this quiz once. But we're just trying to compare the two different lifestyles. So from here, you can take your ecological footprint quiz. After you've taken both of your quizzes, or after you've taken your quiz twice, talk amongst your group to see if there's if your scores like change, if they're different between in your group, and you're just gonna answer a couple questions at the bottom here to just talk about your responses and what you saw. Yes.
So I don't live in a San Francisco residence anymore. I had to move out of that residence, and I'm living at home currently. So do I just take this quiz once, or?
Yeah, so you can just take this quiz once and say that right now I'm back in my regular permanent residence, and that's why I'm only taking this quiz once. So
Okay.
Yeah, the time frame is within this past year. So if your lifestyle within this past year, yeah. Okay, awesome. Did anybody have any questions before I put you back in your breakout rooms? Okay, awesome. I will give you another 20 minutes to do that. And I will see you all at, let's say a little bit more than 20. And I will see you at 10:40. Okay. I will check up on you all in between, but if not, I will see you all then. So I think you all did really well with part B so far. When I was checking in with you in your breakout rooms, it seems like it wasn't too much trouble for you to go over how to do the ecological footprint quiz. But now let me just share my screen so we can go over what's next. For part B, when again, yeah, just like putting your screenshot into part B, and then I hope you got a chance to talk to your group about maybe what's different between your different quiz scores at the end. But at the bottom of part B, there are a couple questions that we can go over together. So for question 5, how accurate is this analysis? It's as accurate as you make it out to be. So as much detail as you put into it, that's as detailed as it could your final results would be for you. But there are some assumptions that going into the analysis that it does take on your lifestyle. So some assumptions are that every every gallon of oil or every gallon of gas that you use in your car is going to have the same amount of emit the same amount of carbon. Or every if you fly, if you've taken the plane within this past year, every jet fuel amount, or every gallon of jet fuel, it doesn't burn the same way. And the same thing if we're thinking about food. So if we're thinking about specifically like chicken, the different types of chicken also have different ecological footprints. So a factory farm chicken, for where you're factory farming, it's very energy intensive. It produces a lot of chicken at the same time, but that the chicken that you eat from factory farms, their ecological footprint is going to be different than if you ate chicken from like a locally sourced, locally grown chicken. If like the amount of time and the distance it had to travel to you and the amount of resources going into that, it's going to be different. So some assumptions is that there are certain parts or aspects of your lifestyle that they assume is going to be consistent across everyone's lifestyle, and in how it's produced, like the resources that's produced for you. For question 7, how do scores vary among your table? Your table is your breakout room. And I hope you got a chance to talk to your breakout room and people within your breakout room. But if not, you can also compare it to the average US 5 Earths. So typically, average US citizen takes up 5 Earths. So is yours lower or higher? What do you think would be the difference? And you can talk about that in question 8, where what factors do you think would be influential? Do you maybe have a longer commute to your job? Do you drive a little bit more than normal? Do you eat more beef versus chicken? Beef has a higher ecological footprint than chicken or fish or even shrimp. So you can talk about what factors do you think was influential in changing your final footprint. And then for question 9, how might you lower your ecological footprint without compromising your lifestyle? So for that question, is there any way for you to lower your ecological footprint without changing your lifestyle? Probably not. So, but what can you do to lower your footprint? So that last question is really to get you thinking about different ways that you can, just thinking about your lifestyle and how you can change your own footprint. But this is really this quiz, you're doing these quizzes is really just to give you a more, give you more awareness about your own choices within your own lifestyle. I think when I first took this quiz, I was like a little shocked by my own lifestyle, my own ecological footprint. So really, it's just to give you more awareness about how you live your life. But for each of these questions at the bottom, you can just answer it in a couple of sentences per question. And now if we're going back to the PowerPoint, we have, again, the deliverables for this lab is that you should turn in your lab 4 responses, that Word doc. So your calculations in part A for exponential growth and part B, your ecological footprint. Again, this isn't due until we meet next week. So at 8:15 on Thursday next week. And you should also upload your water use chart. So starting today, start filling out the water use chart for your for the different water use activities that you do throughout a day, and then upload that to Canvas before lab. Again, this is what it looks like. You can also find this right on the Lab 4 Canvas page. It's right underneath in the same area where you can find the Word doc that you were answering questions in today. Did anybody have any questions about how to do or fill out this water use chart? Okay, awesome. Well, that's pretty much it for Lab 4. Thank you all, and I hope you have a good rest of your week. If you wanted to go over any of your calculations and check up on equations and such, we can do that after class. But overall, hope you have a good rest of your day. Yeah.
Thank you.
Thank you.
Thank you.
Thank you.